Hi, my name's Michael Chandler-Page. I'm a systems engineer here at Cirrus Logic, and in this series of 3 short videos I'll tell you about how we have exploited a 55 nanometer silicon process to get fundamentally better performance from a new high-end analog to digital converter. So in this first video I'm going to talk a bit about the background to the silicon process and the architecture of the ADC. So a bit of history first. Cirrus Logic has been out of the high-end pro audio converter business for a few years now. The last time we designed the ones, they were on 350 nanometer, which is a very old process. And while we've been focusing elsewhere, other semiconductor players have done high-end converters on the 180 process and perhaps more recently on 110. And while that's been going on, we've been developing products and technologies on a 55 nanometer process for high volume consumer applications. And so recently we thought, well, let's get back into the pro audio converter game and using this 55 nanometer process. So on the chart here you can see a comparison of some of the characteristics of the 350, 180 and 55 nanometer processors. If we look at the 55 line at the bottom there, you can see that compared to 180, the digital density and the digital power consumption are both about 10 times better. So what that means is that for the parts of the chip that are implemented in logic, then we get a huge performance improvement there. But also, perhaps less obviously, we get some useful analog attributes on this 55 nanometer process as well. We have better capacitor performance, which is a really big deal for analog design. We have better matching of values, better physical density on the chip, and also we have better parasitic performance. The intrinsic CMOS transistor gain is also improved on 55 nanometer compared to what we were using before. That helps us with dynamic range. And most importantly, we also have much better quality simulation models for the devices on this 55 nanometer process. So those are all positive things, but the headwind we've got here for analog design is that the analog signal headroom has reduced from 5 volts on 180 down to 3.3 volts on this 55 nanometer process. So straight away, that takes 3.6 dB off our dynamic range. So now a quick overview of the architecture that we've used. This is, to be honest, a fairly conventional ADC architecture. The stuff in the dashed box on the left there is the Delta Sigma ADC. The output of that is a 5-bit signal at a sample rate of 6.144 megahertz. And that signal is noise-shaped in the normal way by the Delta Sigma modulator loop in the ADC in order to push the quantization noise of that low-resolution signal up to high frequencies high above the audible range. And then this high frequency signal is converted, high sample rate signal is converted to conventional PCM sample rates by a decimator. This is a configurable digital filter that gives us the familiar 24-bit or 32-bit outputs at 48, 96, 192K and so on. So that's it for the architecture and overview. In the next video, I'm going to talk about how we exploited the 55 nanometer process to create a novel feature for helping control the gain of external mic preamplifiers.